Hello all. Since the fire drill prevented us from finishing our capacitors lecture today, let me talk about charging a capacitor in quantitative terms. As you remember, we ended by talking about how the beginning and end behavior of a capacitor in an RC circuit when a switch is closed, kaboom, is that at the beginning, a capacitor is uncharged, has no voltage difference across it, and acts like a wire. And after a long time, as test questions like to say, after a long time, charge has built up on the capacitor maximally. No further current flows, and so the capacitor acts like a break in the circuit, acts like an infinite resistor. What happens between those moments? Well, let me write down an equation that will let me address this question. If the question is, let's graph as a function of time the amount of charge on the capacitor, we know that it starts at 0 and increases to some maximum value. Well, check it out. If I start here and walk this path in a clockwise direction around the loop, let's write down an equation talking about what I encounter. I first encounter the battery, in which I gain a voltage equal to the EMF of the battery. Let me close my switch there. Once the switch is closed, and I first walk through the battery, then I walk with the current. The battery will drive current around in that direction. I walk with the current through the resistor. So I lose a voltage equal to the current times the resistance. And then I cross the capacitor. And you can tell that I'm losing voltage across the capacitor because I go from some voltage that's greater than 0 to 0 volts, since the bottom side of the capacitor is connected to the battery itself. So this equation describes each moment in the RC circuit. Well, let me work on substituting something for the voltage of the capacitor. We know that the definition of capacitance is that at each instant the capacitance of the capacitor is equal to the charge on the capacitor divided by the voltage difference across it. This means that the voltage difference across the capacitor, this term, is equal to Q over C. So making that substitution, we have that equation. And now, let's see, what have I done here? I've replaced I with dq dt. And indeed, that is what current is. It's the rate of change of charge going past a point. You can also think of, well, Q is the charge specifically on the capacitor. And what is changing the amount of charge that has been deposited on the capacitor? The excess charge, say, on that top plate? It's the current. The current is the time rate of change of the deposited excess charge on the capacitor. This is a differential equation. You can solve it by separation of variables, by getting if you move the constant terms to the right-hand side, then multiply it by dt and divide by the entire right-hand side, you'll get a differential equation that you can solve by separation of variables. By the way, if you find differential equations in general confusing, check out this slide from this lecture in the simple harmonic motion lecture. But hopefully your math class has familiarized you with differential equations, which are very important in physics. We'll solve this by separating variables, and boom, that is the solution. I ask as part of your homework for you to generate that solution. But if this is the time axis, the solution to this differential equation is this, starting off at 0 charge, like we said when we were discussing it qualitatively, and increasing to some maximum amount of charge. Let's talk a little bit more about this function. This is the function that I described, and I'd like to examine what happens with this term. At t equals 0, this term that I've just put into the green box has a value of has a value of 1, right? At t equals 0, e to the 0 is 1, so 1 minus 1 is 0. That's why at t equals 0, there's 0 charge on the capacitor. At t equals infinity, it's like e to the minus infinity, that's 0, 1 minus 0 is 1, so you reach the maximum value there. But let's look at the term that t is sort of scaled by, the coefficient of t. Well, if you express this exponent as minus t over tau, the time constant of the circuit, where tau is equal to the resistance of the resistor times the capacitance of the capacitor, the value of the resistance and the capacitance affects how quickly the charging occurs. If I take just a simplified version of an e to the minus something function, then e to the minus a big coefficient times x falls off very quickly. E to the minus a small coefficient times x falls off more slowly. So would having a high time constant give fast charging, like this blue steep drop-off, or slow charging, like this green gradual process? A higher time constant gives a lower coefficient in front of t, gives a slower charging. Let me say that again. A higher tau, a higher value of r times c, gives slower charging of the circuit. So which of these takes longer to reach the steady state? Well, this one does. You can sort of imagine that qualitatively. It would take more time to load all of the charge onto this big green capacitor plate than it would take to load the charge onto that little blue capacitor plate. It would be slower in the green circuit. Also, and so mathematically, that corresponds to having C be part of tau. Big C, big tau, long time to charge. If the question is, how long does it take the capacitor to charge? The answer is more or less the time constant sort of answers that question. In fact, we know it takes technically an infinite amount of time for the capacitor to fully reach its final steady state charge. But if the question is, how long does it take to get it basically charged? Then the time constant answers that question. At t equals tau, how much of the original current remains? By the way, this expression for current as a function of time came from taking the time derivative of the charge as a function of time function at the top of this slide. Remember, I is dq dt. At t equals 1 time constant, how much of the original current remains? 1 over e times the original current. At t equals twice the time constant is a number of seconds. It's r times c, and that is a number of seconds. At a time equal to twice the time constant, let's see, the current has this value where it's minus 2 tau over t, and that's 1 over e squared times the original current. You can ponder this mathematically to convince yourself that it's right, as you like. But the current falls by a factor of 1 over e when a time of tau passes. This, I would also say that a similar effect happens with the charging of a capacitor, that it reaches its final value. The charge reaches its final charge more by a factor of 1 over e. It's kind of more complicated with the decaying exponential, or with the inverse decay, or the 1 minus a decaying exponential. That's why I asked this question with the current. But what I hope you understand is that tau, the time constant, tells you how long stuff takes to reach the steady state. Great.